Hello and welcome to the 6th live stream of the Science Salon. My name is Danny. I am one of the science communicators at Kyushu University's Public Relations Initiative, and I will be hosting today's Science Salon. And quickly in Japanese, 第6回 Science Salon へようこそ。Danny です。九州大学広報本部のサイエンスコミュニケーターで、今日のサイエンスサロンの司会です。Okay, so to introduce Science Salon quickly, this is a video series where we showcase researchers whose work reflects Kyushu University's Vision 2030 to become a university that drives social change with integrative knowledge. So to kickstart now, I would like to introduce Professor Ekenechukwu Okafor. He is an associate professor from the Faculty of Engineering, and he works on the combustion of carbon-free fuels like ammonia and hydrogen, which contribute to one of Kyushu University's 3 core missions, which is decarbonization. So first of all, welcome to Science Salon. It's great to have you here.
Danny. Thank you very much, Danny, and I'm glad to be here too. My name is Ekenechukwu Okafor, and I'm from Nigeria. Presently, I'm an associate professor here at Kyushu University in the Department of Mechanical Engineering. 皆さんこんにちは。ナイジェリアからのEkenechukwu Okaforと申します。現在は九州大学機械工学部門の准教授として勤めております。よろしくお願いします。Thank you.
Yeah, so thank you very much. So to kind of start off with, so as I was saying, Vision 2030, one of our main missions is decarbonization. It's one of Kyushu University's strengths. How does your research kind of fall into decarbonization? What is decarbonization? Why is it important?
Thank you very much for that question. Decarbonization, as the name implies, is trying to develop systems or combustion systems or energy systems that doesn't depend on carbon as a whole. If you look at the global energy supply and demand presently, 80% or 85% of global energy supply comes from fossil fuels. Fossil fuels are carbon-based fuels. So these fuels contain carbon. When you burn them to produce energy, you have that carbon being oxidized and you have CO2 being produced. So we know that CO2 has a global warming potential. Okay? It leads to global warming. So when you have a lot of CO2 being produced in the atmosphere, you have this global warming effect being promoted. So that's why when you have because of our high dependence on fossil fuel, we are heating up our environment. So the idea behind decarbonization is to reduce CO2 emission or to develop fuels or energy systems that has no dependence on carbon. So in future, we'll be having energy systems that has no CO2 emission, okay, and then we can say that we can reduce or prevent the promotion of global warming. Okay.
So we kind of have some fuels that are like the fuels of the future, candidate fuels like hydrogen and ammonia.
Okay.
What are the kind of current challenges that are stopping us from being able to utilize them right now?
These fuels, hydrogen and ammonia, are relatively new fuels. I'll say relatively. Hydrogen has been there for quite a long time as a fuel though, but we don't have a lot of combustion systems using hydrogen. Ammonia, on the other hand, is a new fuel, entirely new fuel, because we've been using ammonia as a manure, as a material for manure production,
right? Yeah.
Fertilizers, okay? So, but recently we're trying to use ammonia as a fuel. So the reason why we can't use them now, or we've not been using them, is because one, there are some challenges. Actually, there are challenges to the application as fuels. Okay, even though these fuels are carbon-free fuels, if we use them, we can easily achieve our decarbonization goals. But their combustion properties, okay, there are some challenges with their combustion for instance, for ammonia is difficult to burn. Okay, so up until now, we don't consider ammonia as a fuel.
I mean, that's probably a good thing when you think about using it as fertilizer, right?
Okay, yeah, that's good. So your fertilizer wouldn't be flammable, right? Okay. So that's a good thing for ammonia as a chemical that we can use for other things. But this time around, we are looking at it as a fuel. So in that case, because it's not easy to burn, when I say it's not easy to burn, it means that the easiness or the tendency of a flame to burn, okay, the ease of a flame to burn, of a fuel to burn, is measured by what we call the burning velocity. Okay?
Burning velocity.
Yeah, how fast the flame can burn. For instance, if we have a fuel and an oxidizer in this room, they are mixed, and you ignite the mixture somewhere. You just light a match. What would you expect to have? It's going to be
a big eruption, right?
Something like that.
Yeah, big explosion.
So you're saying big explosion because you're thinking that this fuel is going to propagate very fast, right? So the speed of the flame, the propagation speed of the flame, is what we call the flame speed or the burning velocity. It's related to the burning velocity. For ammonia, you might be surprised that when you feel ammonia in this room, mix it with air, and you ignite a match, you'll be surprised it might not burn.
Nothing happens?
It will be difficult to burn. Yeah. So because the burning velocity is very, very low, very small, so it's difficult to burn ammonia. So, but we need to develop combustion systems for this fuel.
So if ammonia is so difficult to burn, why are we thinking to use this as a candidate fuel rather than hydrogen?
Okay, that's an interesting question. See, we are also looking at using hydrogen as a fuel. Okay, so in my research, I'm looking at hydrogen as a fuel also. I'm developing combustion systems for hydrogen. I'm also studying the fundamental properties of hydrogen as a fuel. But why are we looking at ammonia? The reason is because even though the important or the important energy vector we want to use in future is hydrogen, because in the future decarbonized society, we're going to have, the plan is to have a lot of renewable energy. We are going to have introduction of a lot of renewable energy. So we're going to have energy production from solar cells, energy production from wind and other sources, okay? And these energies, we also need to save them and transport them, right? Okay, for instance, Japan has a low energy security, right? About 12%. So they still need to import a lot of their energy into Japan. So in that future where most of the energy will be renewable energy, we still need to have a way to import renewable energy into Japan, okay? So when we want to import renewable energy, we have to convert. The best way to store renewable energy and to transport it is to convert it into chemical energy. So what I mean by that is we convert renewable energy like energy from the sun, solar energy, is usually in form of electricity, right? When you have insolation, it's converted to electrical energy. Now, if we want to save this electrical energy, the best way to save it for a long time and transport it is to convert it into hydrogen.
Okay.
So what you do is you use this energy to split water using electrolysis. So when you split water using electrolysis, you produce hydrogen. Okay?
And that means that you have energy even when the sun's not shining,
Very good.
or when the wind's not blowing,
Yes.
or when the waves aren't, waving.
We don't have that. Yes. So that's the idea. So now we have hydrogen being produced. Okay, so that's the way we're going to store this energy. Now, when we want to transport hydrogen over long distances, for Japan is thinking of buying hydrogen from countries like Australia or the Middle East or even America. Also, they're thinking about North Africa. So it's going to involve long distance shipping. In that case, if you want to transport hydrogen as hydrogen, it's not economical because hydrogen is a very light gas. If you want to transport a lot of hydrogen, you have to make it a liquid. To make hydrogen a liquid, you need to reduce the temperature to negative 253 degrees centigrade.
That's very cold.
That's very cold. That's cryogenic.
And I'm guessing that requires a lot of energy.
Yes. It requires a lot of energy, and to maintain it at that temperature is also very difficult. So if you don't maintain it at that temperature, you're going to have boiling off of the hydrogen. So let's say you're transporting hydrogen from Australia to Japan. Along the way, you have boil off, and you have to like release it. When you have boiling off, you have to release the gas, because if you don't, the container where you have the hydrogen, the pressure is going to increase to very dangerous levels, and you could have an explosion. So you keep releasing the hydrogen on your way from Australia to Japan. Maybe by the time you get to Japan, you don't even have any hydrogen in the tank.
Yeah.
Okay, so that's not really. So one of the ways we want to transport hydrogen is as ammonia. Okay, so we know that by Haber-Bosch process, when you combine hydrogen with nitrogen from air, you can produce ammonia. Now, why ammonia is easier to transport and store is that ammonia becomes a liquid at just negative 33 degrees centigrade. It's already a liquid. Or if you compress it to about 8.5 bar, it becomes a liquid. So it's easier to carry. And one more important thing about hydrogen is that hydrogen contains more ammonia. Ammonia contains more hydrogen than hydrogen itself, than liquid hydrogen itself. Okay, so to give you a perspective, let's say you have 1 meter cubed, 1 meter cubed, of gaseous hydrogen. Okay, you want to transport this gaseous hydrogen. If you make it a liquid, if you convert it into a liquid, like cool it to negative 253 degrees centigrade, it becomes a liquid hydrogen. Or you can use that hydrogen and produce ammonia. Okay, the size of the liquid hydrogen, if you compare it to the size of the liquid ammonia that is containing this hydrogen, the ammonia is much smaller. Okay.
So within a given volume of a ship, you can transport a lot more hydrogen atoms as ammonia.
Yes.
I see.
Okay. So that's why ammonia is considered one of the most advantageous hydrogen carriers. Okay. So to transport hydrogen, there are a lot of carriers that are being considered because it's difficult to transport hydrogen, also to store it for a long time. So we are considering a lot of carriers like hydrogen. Metallic halides for hydrogen storage and transportation. But of all these carriers that we have, ammonia seems to be the one with the greatest advantage. Okay? So the thing is then, when you transport hydrogen in terms of ammonia and bring it to a country like Japan, you can still convert it back to hydrogen. Okay? So, but every time you convert energy from one form to the other, there's always a loss, right? Okay. Yeah. So in my research, I'm thinking of, instead of converting it back to hydrogen, why don't you use that ammonia directly in combustion systems? Okay. So that's why I'm trying to develop combustion systems that's going to burn ammonia directly instead of now transporting it, converting it back to hydrogen. Okay. So it's.
Is this quite a radical idea, or are quite a lot of scientists working on ammonia as a fuel?
There's quite a lot of scientists working on ammonia presently, but this idea of ammonia combustion, this research on ammonia combustion actually started in around 2014. There was a Japanese government project called the SIP Energy Carriers Project, where amongst the project groups there was a group that was looking at ammonia direct combustion. Okay. Back in the 1960s, the American government tried to develop combustors or gas turbines for ammonia.
Oh, okay.
So that research was done.
So this idea has been tried before?
Tried before, but because they found out that it was difficult to burn ammonia. They found out that the combustion efficiency was very low. So that research was stopped, it was abandoned. So it was during that Japanese government's project that was started in 2014 that we rekindled this interest again in ammonia as a fuel. And during that project, we were able to find out that there's a way to actually burn ammonia efficiently in combustion systems. So from our research here in Japan, then I joined that research after my PhD. I joined the research in 2015. That's when I started my research on ammonia combustion. Okay. So I started out research in Tokyo University. So since then, the research on ammonia combustion has spread all over the world, and a lot of researchers in combustion field are looking at ammonia combustion now. Yeah.
So it's becoming a more popular idea.
It's quite a popular idea in the combustion society.
So Which one do you think? So is ammonia going to be kind of a gateway fuel to hydrogen, or do you think it has the potential to become a fuel that kind of replaces hydrogen?
I wouldn't say that it's going to replace hydrogen, okay? So that's why I said I'm working not just on ammonia combustion, I'm also looking at hydrogen combustion, okay? Yes. So there's no single fuel that is going to help us achieve our goal of one, energy diversification, fuel diversification, and also carbon neutrality. So we are looking at different kinds of fuels. The possibility of using ammonia is there. The possibility of using hydrogen that is there too. And we're also looking at other kinds of fuels like biofuels in trying to achieve this carbon neutrality target by 2050. So ammonia is not going to replace hydrogen, and neither will hydrogen replace ammonia, okay?
I was wondering, are there some situations where hydrogen is better or ammonia might be better? Like if you're talking about an airplane engine or a gas-powered turbine, are there certain situations which might lend themselves better to ammonia or to hydrogen?
Yes, there are for situations where you have, I would say, for instance, for rocket engines, for instance, okay, where you're going to be having very fast flows. I think I have to explain what I mean by flows. Okay, let me step back a little bit.
Okay.
To understand the difference between hydrogen and ammonia as fuels, while they have different challenges. Okay. When you turn on your lighter, okay, let's say, or let's say if you're using a stove back home to cook, you turn on the stove and you have light, have fire on your stove.
Yeah.
That's usually what happens. That's how we cook, right?
Yeah.
Imagine when you turn off that, when the light goes off and the stove is still on, but there's no fire on the stove. What you have is just a flow of the gas, right?
Yeah.
Okay, so what actually happens is that a flame is just a sheet that is on a flow. It's a reaction sheet stabilized on a flow. What I mean by that?
Flow of gases, and then the flame is on top of this flow?
That's good. That's what it is. So you have, that sheet is a sheet where chemical reactions are taking place, because combustion is simply the reaction of a fuel and an oxidizer that produces heat, okay? So this reaction takes place in a sheet. That sheet is stabilized on the flow for the burners. So whenever you look at your burner and you have a flame on the burner, what it means is that there's a flame stabilized on that burner that is reacting, is a reaction sheet where the fuel and the oxidizer are reacting. So that sheet consumes, let me use the word, consumes the fuel and the oxidizer, okay?
Okay.
Now,
so just to clarify, so there's a flow of gases,
yeah,
and there's a flame on top, and the flame consumes the gas as it flows past.
Okay, very good. So you better look at it as there's a flow of gases, there's this sheet. The gas is passing through the sheet. As it's passing through the sheet, it's consuming it, okay? So now, this flame has its speed. It has its own ability to move, okay? Just as I told you that when you ignite something here, it's going to move, right?
It's going to move fast, or it's going to move slow.
So this sheet is trying to consume the flow, okay? So it's trying to move towards the flow to consume it while the flow is coming out. But usually what you have in your burner is a stable flame, right? So the flame is stable. What it means is that the speed of the flow and the burning velocity of the flame are almost the same. So that's why you have a stable flame, okay? So imagine a situation where the burning velocity is very low. What's going to happen is that this flow is going to carry the flame away, okay?
Okay.
Let me use another analogy, okay?
I'll take your word for it.
let's say you are in a gym. You're running on a treadmill, okay?
Okay.
Usually, one thing you're careful about when you run a treadmill is to stay stable, right? Not to fall. But actually, you have a velocity, right? You're running with a velocity. And that velocity seems to be equal to the velocity of the treadmill, right? When your velocity and that of the treadmill are the same, that's when you become stable, right? That's what happens, right? That's what happens in the flame. You are the flame there, and that treadmill is the flow.
So if the treadmill is too fast for my running speed, then it will topple over and the flame will go out.
That's good. That's good. So that's what happens. So now, coming back to hydrogen and ammonia, hydrogen has a very fast flame speed. It's so fast. Ammonia has a very low flame speed, okay? So now, the conventional fuels that we have, the conventional hydrocarbon fuels that we have, they have a flame speed, average flame speed of about 40 cm per second, around 40 cm. Centimeters per second, okay? Around that. There are methane, natural gas, or something below that, about 35. But let me on average, they have about 40. Hydrogen has a burning velocity that is more than 200 centimeters per second, okay?
Very fast.
Now, ammonia has a speed of 7 centimeters per second. Okay?
Yeah.
So in combustion systems where the flow speed is going to be very fast, very high, like in rocket engines, it might be easier to use hydrogen than ammonia because hydrogen can survive very fast flow fuels, while ammonia need a little bit of slow flow fuels. Okay? So these are areas where we could have differences in the way they are applied. But we're also looking at possibilities of improving the flame speed of ammonia. There are some things that we do, like enriching the air. Instead of burning ammonia in air, we burn ammonia with air enriched with oxygen to increase the flame speed.
So this is what your research is specifically looking at, right? Like how to increase the flame speed and the flame stability of ammonia?
That's it, yeah. I'm looking at how to improve the flame stability and also how to control emissions from ammonia flames.
Just for our Japanese viewers out there who may be struggling with some of our terminology, do you think you could quickly sum that up in Japanese?
Okay. 私の研究についてなんですけれども、現在はアモニア燃焼研究について、取り組んでおりますけれども、そのアモニアなんで重要かというと、アモニアは炭素が入ってない燃料、炭素燃料という燃料なんですけれども、アモニアの燃焼技術を開発すれば、脱炭素社会の実現ができるということです。アモニアは燃焼速度が非常に低い燃料なので、バーナーとかガスタービンのバーナーとか燃焼機に安定化させることが難しいという問題があります。今回私の研究の中にアモニアはどういうふうに安定化させるかという、研究課題を、検討しております。アモニアも水素も私も水素のことを、検討してるんですけども、水素燃焼のことも検討してるんですけども、水素の場合は燃焼速度が非常に、高いので、貝の安定化で、とよりも貝のコントロール問題もあります。そういう、研究課題について今研究しております。I don't know if I should continue explaining that. Okay.
I think that's good. So you're trying to stabilize flames. What is currently your biggest challenge in your research to achieve this?
One of the biggest challenge in my research presently, of course, is as I explained, stabilizing ammonia flames is quite challenging, but we found ways to stabilize it. But there's one other interesting problem with ammonia combustion. Ammonia contains nitrogen in its molecule, right? Yeah. It's NH3, right? So when you burn ammonia, you produce nitric oxides.
Yes.
Okay, you produce NO, N2O, NO2. These are
for our viewers, what are nitrous oxides or nitrogen oxides?
Okay. These are oxides of nitrogen that have detrimental effects on the environment. Okay, like NO could lead to acid rain. N2O, on the other hand, has a global warming potential that is 300 times more than that of CO2.
So this is a molecule that can be formed.
These are molecules that can be formed when you burn ammonia.
When you burn ammonia.
Okay? So one of the problems we're trying to solve is when we burn ammonia, we have to find a way to reduce these molecules. Okay? So we're trying to find ways to reduce these molecules in ammonia combustion. It's one of the biggest problems that we have presently, because the first problem you solve when you're trying to develop a combustor is stabilizing the flame. Okay? You have a stable flame. When you have a stable flame, now you look at what are the kind of things that are produced in this flame? What are the kind of emissions that come out of this flame? So the emissions we're looking at now with ammonia combustion is that NO, N2O, and NO2. Okay, we're trying to see how we can control these emissions.
So by turning to a renewable fuel, you could actually make the global warming situation worse if you don't control
N2O.
NO2O.
N2O, yes.
N2O.
Yes.
N2O.
Yes.
難しいね。
そうですね。なんかアモニア燃焼では、窒素酸化物がアモニアを燃やしたら窒素酸化物が生成される、恐れがあります。その窒素酸化物の中に N2O という、排出量が廃棄物があります。その N2O は、地球温暖化効果もあります。N2O の地球温暖化ケースは CO2 の地球温暖化ケースの300倍でありますので、アモニア燃焼技術を開発するときに N2O とか NO の排出量を削減することが、研究課題になっています。はい。So this is one of the things we're trying to solve. Just to give you a perspective on that, also in conventional hydrocarbon fuels like gasoline or natural gas, when you burn these fuels, nitrogen oxides or oxides of nitrogen are also produced. Okay, so we usually call them NOx. Okay, NOx is also produced in conventional hydrocarbon fuels. But the way NOx is produced in conventional hydrocarbon fuels are different from the way NOx is produced from ammonia fuels. In hydrocarbon fuels don't contain any nitrogen in the molecule, right? So the only way NOx can be produced is the nitrogen in air gets oxidized at very high temperatures. So you have NOx being produced that way, okay? So in that case, if you can reduce the temperature of the flame, you have lower production of NOx. So up until now, before we started doing ammonia combustion, most of the NOx that we know are called thermal NOx. They are produced due to high temperatures. Okay? High temperatures lead to nitrogen in the air being oxidized by oxygen, leading to NOx production. But now in the case of ammonia, thermal NOx is not that important, okay, because ammonia already has nitrogen in its molecule. So in the case of ammonia, even at low temperatures, when you burn ammonia at low temperatures, you still have a lot of NOx being produced. Okay? So reducing the temperature alone does not solve the problem of NOx in ammonia combustion. We're trying to look for other ways to solve it.
So what are some of these other ways that do you try and trap the NOx after it's formed, or are you trying to change the chemical process so that they're not produced in the first place?
That's a very interesting question, because we are using both methods. Okay. Yes. One of the ways to control NOx is, as you mentioned, trapping the NOx after it's been produced. Okay, so that's one of the methods that has been used for quite a long time, where we have what we call the denox process, where after producing the NOx, you could use some agents or catalysts to try to reduce the NOx. But one of the methods we're using, mostly in the case of ammonia, we try to use a sort of chemical process, which is during the combustion process, there are some conditions that don't produce NOx. Okay, so depending on the quantity of fuel and oxidizer, the ratio of the fuel and oxidizer you burn, there are ratios that doesn't give you a lot of NOx. Okay, so we're trying to burn at those conditions. But there's a catch, okay? When you burn at those conditions, they don't produce NOx. Most times you produce a lot of unburnt fuel.
You produce a lot of unburnt fuel?
Unburnt fuel, okay? You produce a lot of unburnt fuel, or you produce a lot of hydrogen in the flame. So these are unburnt fuels, meaning the combustion efficiency is very low. So what we do is, in gas turbines, we're using a method called two-stage combustion, where we can sort of divide the combustor into two stages. The first stage, we burn it at a condition where you don't have NOx production, but you have a lot of unburnt fuel coming from that condition, okay? So then this unburnt fuel moves to the second stage, and then you put in a lot of air to burn them off. So at the end, you get very low NOx emission.
So you kind of recycle the fuel twice?
That's what it looks like. Okay, yeah. So you have very low NOx emission at the end.
Do you want to quickly just explain that in Japanese?
Okay. アモニア燃焼では NOx の排出量削減方法とし、については、ガスタービン燃焼機で二段燃焼という燃焼方法がありまして、二段燃焼何かというと、ガスタービンの燃焼機は、二段に分けます。最初の、一段流力では、ちょっと燃料が濃い塗料比、ちょっと燃料が濃い条件でアモニアが燃焼すると、あまり NOx の排出量が少ない、NOx の生成速度が少ないから、あまり NOx が生成されない条件になります。でも、この NOx が生成されない条件ですと、たくさんの、未燃燃料、燃えてない燃料が生成されます。燃えてない燃料とか、水素も生成される条件になります。けれども、だから一段燃焼では NOx の生成量が低いんですけれども、未燃部と、水素がたくさん生成されます。じゃあ一段燃焼から一段流力から生成された、水素と未燃部は二段燃焼に来たらたくさん二段空気を導入します。二段空気導入したらその燃えてない燃料とかを燃やします。それすると、燃焼機の出口では NO の排出量がある程度低くできます。それは、NOx の排出量の削減手法ということですね。二段燃焼ということです。
なるほど。
そうだから二段燃焼は、塗料比という燃料と酸化剤の割合のコントロールをすれば NOx の排出量削減ができるという手法です。
So now I kind of want to move on slightly to how you kind of originally got into this field. Like, what kind of drew you as a child to becoming a scientist? Were you always interested in science?
As a child, I didn't actually start out wishing or desiring to be a scientist, but I had a passion for cars. I loved cars. I still like cars a lot these days. So I wanted to be an engineer in the beginning. I want to design cars. I wanted to make cars. That's the reason I got into mechanical engineering. So I studied mechanical engineering in my undergrads, and during my undergrads, I did a 7 months internship in a car manufacturing company. That was a Mercedes-Benz trucks manufacturing company, though. Yeah, so yeah, I did that, and it opened me up more into this technology, automobile technology, and I really wanted to learn more about automobiles. Okay, so that's why when I came to Japan, I wanted to study more about automobiles. So the proposal that brought me to Japan was I wanted to study ethanol combustion in engines.
So ethanol is one of those biofuels, right?
Yes. Yeah. So I've always had this interest in carbon neutral fuels. So I wanted to study ethanol combustion in engines. Okay, so that's what brought me to Japan. And the idea was not for me to continue as a scientist. Okay, I just wanted to learn more about this technology and just get into the field and start making cars and designing cars. That was the idea. But I think The more you study, I think when you get into graduate school, the more you study, the more you get roped into research because I found that the more I studied, the more I found out that there are things I needed to know that I didn't know. So I wanted to know more about it. I'm quite curious, okay? So after my master's, I was like, I needed to learn more. I've not had enough of it. So I went for PhD. And during my PhD, I was like, I think I'm meant to be a researcher. So I continued.
You got sucked down into the whole of academia.
I think that's how it happened, okay? So, yeah, that's how it's been. I didn't really start out wishing to be a scientist. I wanted to be an engineer. And the work I was interested in, which is internal combustion engines, car engines, what I'm doing now is a bit far from it, a bit different from it, okay? Because I'm focusing on gas turbines mainly this time. But some of the fundamental work I'm doing can still be applied in reciprocating engines because I'm looking at flame propagation, how fast a flame burns and what affects how fast it burns.
So one day we could have cars that run on ammonia.
Of course, there are some people looking at that already.
Yeah.
Yes, hopefully.
So you were actually a PhD student here, right, at Kyushu University?
Yes.
Yeah. How have you found it now that you're back as an associate professor? What was that kind of journey like for you?
It's been an interesting journey, I will tell you. It's been an interesting journey. I joined Kyushu University in 2010 as a master's student, and then I finished my master's, got a PhD in 2015. Then I left Kyushu University. I got a job at Tohoku University. That was during the SIP project, SIP Energy Carriers project. So it was in Tohoku University that I started my research on ammonia combustion. Okay, so I stayed in Tohoku University for about 3.5 years, worked there. After that, I moved to AIST, National Institute of Advanced Industrial Science and Technology. There I continued my research on ammonia combustion, but then in gas turbines in large-scale facilities. It was more of applied research that I started doing there. And I worked with AIST for about 3 years and got back to Kyushu University in 2022. That was January 2022, okay? So comparing when I was a PhD student and now that I'm an associate professor at Kyushu University, a lot of things have changed, actually. Yeah, it's been an interesting journey, but when I came back, of course, my responsibilities are now quite different, right? Because then I was a student. Now I'm an associate professor. I have a lot of students under me that I'm supervising. I don't just do research. As a PhD student, I only did research, okay? I concentrate on my research. Now I have research responsibilities. I have responsibilities to teach classes. I have a responsibility to supervise my students. I also have a responsibility to work as an administrator in the department. Okay, so it's quite different. Okay.
And you teach your classes in Japanese, right?
Yeah, I teach most of my classes in Japanese. Yes. It's easy. It's easier for me to teach Japanese classes because when I talk to my students, I talk to them as if I'm talking to friends. So casual Japanese is okay for me. But when it comes to very formal Japanese language, I think it's a bit difficult.
Like
I struggle with that, yes. Yeah. I struggle with that. Yeah, so teaching Japanese classes is not that difficult for me. Okay. Yes.
When you first came to Japan, to Kyushu University, did you have any level of Japanese at all?
Okay, no, I didn't have any level of Japanese. It was zero Japanese language abilities. But Kyushu University had this a program they called tutorship program, where every international student was assigned a tutor. Okay, so I was assigned a tutor, a Japanese student, a senior in my lab. So he helped me a lot in the things I did. So even though I didn't speak Japanese, I could settle in easily using his help. Okay.
So there was some support there for you.
There was very good support, yes. Although even though I had support, there were times I had issues with not understanding the language. You see, in 2010 we didn't have smartphones. Okay, so we didn't have translators for Japanese language. I remember there was a time I wanted to buy body cream. And I told my lab mates, some guys in my lab, they were quite willing to take me to Gakentoshi to the stores there to buy body cream. We came back with something I thought was body cream, but when I used it, I took a bath, I used it, and I just turned white.
Oh,
I didn't know, why is this different? This is supposed to be a body cream. So I tried to read the kanjis, the Japanese characters on that bottle. Finally found out that what I bought was bath milk.
Oh.
So, you know, so there were instances like that where I had little problems with the language and made some mistakes, okay?
Yeah, we've all been there, I think.
Yeah.
But what made you stay in Japan?
Okay, that's quite an interesting question. After my studies, I thought I still had a lot to learn, one. So I wanted to continue researching. So that's why when I joined Kyushu Tokyo University, I joined as a postdoc. And the research we're doing then in Japan, that's when we started ammonia combustion research. Japan was the only place doing it then. It was started in Japan, ammonia combustion, this new phase of ammonia combustion. I wanted to be part of that because it keys into my objective or my passion. I've always wanted to work to develop combustion systems for carbon neutral fuels. Remember, I came to Japan to study ethanol. So when I heard about ammonia, it was something that I really wanted to study. So I wanted to be part of that project. So that's one of the reasons I decided to stay and work on that project. When I stayed, I fell in love with this country, of course, from my master's. You know, the way things are done here. The Kyushu University is, why I even chose to continue my PhD in Kyushu University was, of course, because of the high-tech equipment we have for research. Okay, so I think my decision to stay basically was because of the kind of research we do here in Japan. You know, I really liked to stay and learn more. And then when I stayed, a lot of things fell into place. I got married, and my wife is also Japanese. Okay, so there's a lot of things to love about this country.
So you put a lot of roots down.
Yes, definitely. Yeah. Yes.
So great. So, yeah, moving forward, you came back to Kyushu as an associate professor.
Yeah.
And you were in the same lab, right, that you were in
the
as
same
your PhD?
laboratory I graduated from, yes.
How is it working with your supervisor from a student to an associate professor?
That's interesting. I don't think our relationship almost remains like how it's always been. We had a very cordial relationship when I was a student. I think I was his first international student, PhD student, okay? And our relationship was very, very cordial, very good. So when I came back this time, we still have a very cordial relationship. Sometimes he calls me Okafor-kun. You know, that's what he calls me when I was a student, okay? And when we're talking on personally, when we're just alone, he refers to me as Okafor-kun. But in front of the student, he calls me Okafor-sensei. Like, yeah, you know, I used to be your student, you know? Yeah. So it's great working with him. Yeah. It's been great. Right from one of the reasons I even considered coming back to work with him was because we had a very good relationship going from the beginning. Okay, so yeah, I like it here. Sure.
The other thing I wanted to touch on is the kind of international student associations. Okay. So as a student, you formed the Kyushu University African Society, right?
Oh yeah, that's interesting. Yeah, when I was a student, sometime in 2012. We formed an association for African students in Kyushu University. We call that ASCU, Association of African Society of Kyushu University, that's ASCU. We formed that association to bring all Africans in Kyushu University together, not just the students, but also workers or people that have affiliations with Kyushu University, to bring them together under one body to be able to better care for our welfare, okay? That's one of the reasons why we formed ASCU. It's been there since 2012 and it's still waxing strong now.
And you're still involved with the society now, right? You're the patron?
Yes, presently I'm the patron of ASCU. The patron of the association. We have quite a large number of African students as members from different countries in Africa. Yes.
What kind of activities do you get up to with this association?
One of the objectives of ASCU is to disseminate information about Africa to the Japanese public. Okay, for people to get to know Africa from our own perspective. Okay, for us telling our own stories. So ASCU organizes our events to achieve that aim. So sometimes we organize social events where we invite people to come and have fun with us. We organize academic events, like sometimes we organize seminars for the members, seminars on how to, for instance, write academic papers, on how to network. These are very important things for researchers. We also have events like welcome parties, send forth parties for the members. One of the activities we used to have before COVID, we used to have Celebrate African Day here at Kyushu in Fukuoka.
African Day,
yeah.
I didn't know this day.
Okay, yeah. We came up with that idea usually in March. Sometime, I think 20th or 21st of March here in Japan is usually a public holiday. So we usually use that day as African Day. So we organize an event for the public to come and learn a lot about Africa. During that event, we do presentations from different countries in Africa. We invite dignitaries from our embassies to join us. And I think it's usually one of the biggest events that we organize. We use it to disseminate information about Africa to the general public. And one other objective of ASCU is we want to use this platform to spread information about academic opportunities here in Japan to other Africans back home. So
there's a connection between the kind of Kyushu University here and a lot of African universities.
Yes, it's like a bridge between Japan and Africa. That's what we're trying to create.
Have you seen like an increase in the number of like students from Africa since ASCU began?
Yeah, there's been an increase in the number of African students. Presently, we have quite a lot of Africans coming from East Africa. Probably there's a program that's making it possible for students, a lot of students, to join Kyushu University. And whenever these students come, we seek them out. We tell them there's an association here like ASCU for you, and they're always willing and very happy to find a family here, and they join. So we have almost all the Africans here in Kyushu University are members of ASCU. The numbers are growing, yes, over the years.
It's nice. It's good to kind of find a good community away from home.
That's true. Yes.
Yeah. All right. I think that's all we have time for today. But it has been really wonderful to hear more about your research and your kind of efforts to help internationalize Kyushu University. So thank you very much for joining me, Ekene.
Thank you very much, Danny. It's a pleasure.
And thank you for joining us too. Good night.